The traditional route to a career in engineering or design often involves years of schooling, student loans, and rigid academic schedules. While these can provide structure and credentials, they also come with limitations. By contrast, a self-directed learning approach offers the flexibility to learn at one's own pace, tailor the curriculum to personal interests, and develop a portfolio of work that showcases real-world problem-solving skills. This approach is not about cutting corners but rather about creating a personalized education. Building a project such as a miniature robotic machine is more than just an exercise in design. It's a process of experimentation, simulation, iteration, and innovation. Even without constructing a full-scale prototype, the process itself demonstrates mastery over essential engineering principles like kinematics, load dynamics, and vibration analysis. For someone without formal education in engineering, this approach serves as both a substitute for and a complement to traditional education. It allows for the cultivation of practical skills, which are highly sought after in the industry, and provides tangible proof of one's abilities, an invaluable asset for job applications and entrepreneurial pursuits. One of the challenges for self-directed learners is finding affordable tools that match the functionality of industry-standard software like SolidWorks. While SolidWorks remains a powerhouse in the CAD world, its licensing costs are often prohibitive for individuals. Fusion 360, developed by Autodesk, provides a compelling alternative. It is not only significantly cheaper but also offers a comprehensive suite of tools for 3D modeling, simulation, and manufacturing. Fusion 360 is particularly suited for self-directed learners because it is cloud-based, making it accessible across devices and ideal for collaborative projects. Its integrated simulation tools allow for finite element analysis, FEA, and motion studies, enabling designers to test the structural integrity and dynamic behavior of their creations without the need for expensive physical prototypes. Moreover, Fusion 360's community resources, tutorials, and forums make it an excellent choice for individuals teaching themselves design principles. The software's user-friendly interface and robust capabilities mean that a self-directed learner can achieve professional-level designs with relatively little upfront cost. While CAD software like Fusion 360 handles design and structural analysis, Python offers the ability to simulate and control the behavior of a machine. Python's libraries, such as numberpy, matplotlib, and scipy, can be used to simulate mechanical systems, analyze kinematic equations, and predict how a machine will respond to different inputs. For robotics projects, Python's integration with frameworks like ROS, Robot Operating System, allows for the development of control algorithms and real-time testing. Python's versatility extends beyond simulation. It can also be used to write the software that powers the machine itself. For instance, Python can be employed to program a miniature robotic machine to perform specific tasks, providing hands-on experience in both software and hardware integration. This dual capability makes Python an indispensable tool for anyone pursuing mechanical design and engineering. Building a miniature machine, whether it's a robotic arm, an automated conveyor system, or a mechanical prototype, offers a cost-effective way to gain hands-on experience. Miniature builds allow for testing of concepts like load dynamics and vibration behavior on a smaller scale, with mathematical extrapolations used to predict performance at full scale. Miniature prototypes are also highly practical for showcasing skills. Employers or collaborators are far more likely to be impressed by a functioning small-scale machine, complete with software and control systems, than by theoretical knowledge alone. The process of building, testing, and refining a miniature design demonstrates a deep understanding of engineering principles and a commitment to hands-on problem-solving. In the world of design and engineering, a strong portfolio often speaks louder than degrees or certifications. By documenting the process of designing and building a miniature machine, from initial sketches to final testing, a self-directed learner can create a portfolio that showcases their abilities in CAD design, simulation, programming, and mechanical assembly. Even if financial constraints or logistical challenges prevent the construction of a physical prototype, a well-documented digital portfolio can be equally impactful. Including simulations, animations, and analysis results from tools like Fusion 360 and Python adds depth to the portfolio, demonstrating both technical skills and a capacity for innovative thinking. The financial advantages of this self-directed approach cannot be overstated. The cost of tools like Fusion 360, Python, free and open source, and materials for miniature builds is significantly lower than the cost of even a community college education. This approach allows for flexibility. Projects can be scaled up or down based on budget and time constraints. Moreover, the skills gained through this process are directly transferable to CAD design jobs, freelance opportunities, or even entrepreneurial ventures. Building a career in mechanical design and engineering through a self-directed approach is not just a viable alternative to traditional education, it's a powerful statement of independence, creativity, and determination. By leveraging tools like Fusion 360 and Python, and focusing on practical, hands-on projects like miniature machine prototypes, I can gain the skills and experience needed to succeed. This journey is not just about saving money or avoiding debt, it's about taking control of my future and creating a portfolio that reflects my unique talents and vision. Whether I use these skills to secure a CAD design job, launch my own projects, or even apply to prestigious institutions. The project for Fir'mv Morse is a significant undertaking aimed at building my professional portfolio. The foundation of this work involves learning essential skills in databases, Python, Blender for graphics, and website building. Although I'm focusing on the basics, the real emphasis is on fundamental aspects that align with my career goals in CAD designing and engineering technology. This includes designing mechanical systems with a deep understanding of manufacturability and functionality, which requires extensive research and hands-on experience. To succeed, I'm integrating disciplines like trigonometry, the philosophy of math, and language to connect ideas and understand their interrelations. This project is ambitious, as I aim to bypass traditional college education by self-teaching and creating this portfolio independently. A significant part of this involves Python programming, where I've already created a simple code to process human body measurements for clothing design. The program allows a user to input measurements, which are then matched with clothing designs in a database, enabling custom-fit designs. Currently, I use pythonanywhere.com for programming due to my limited hardware capabilities. My coding efforts involve learning to use MySQL databases within Python environments. By linking Python scripts to databases hosted on platforms like Python Anywhere, I can execute queries, manage records, and automate operations. I'm also integrating prior knowledge of clothing design, such as draping and pattern creation, into this programming initiative, blending it with engineering concepts. Although I'm not a professional programmer, I'm learning these skills to complement my CAD design focus. The modern job market demands interdisciplinary expertise, which is why I've worked on understanding coding syntax, databases, and AI. For instance, AI serves as a translator, helping to convert ideas into practical, programmable solutions. MySQL and Python integration plays a critical role in my project, enabling me to manipulate data and streamline processes. Although Python Anywhere offers free features, advanced capabilities require payment, which limits my current setup. Nevertheless, I approach learning with a project-first mindset, mapping out my goals in advance. My CAD portfolio will be comprehensive, requiring substantial investment and months of dedicated work. Ultimately, my goal is to design an automated clothing system that incorporates robotics, physics, kinematics, software engineering, and database management. This ambitious project is showcased on my YouTube channel, where I've shared initial ideas and visual concepts. It's not just about mechanical systems but a holistic approach that merges multiple disciplines, reflecting the multifaceted nature of modern engineering and design. I'm not going to sit here and try to remember Python syntax. The whole idea is that Python is a tool, just like MySQL is a tool, AutoCAD is a tool, or any other software. Everything you do stems from creativity, problem-solving, and logic. That gets translated into a language, such as Python, or into lines, circles, and squares in AutoCAD. For me, the focus is on creating the logic first. When I approach a problem, I think about the logic behind it, not the syntax. Let me demonstrate. Before even thinking about syntax, I need to establish the code logic. Typically, you'll have an input and an output. This is where algorithms come into play, which I've been studying, things like logarithmic thinking and similar concepts. In any algorithm, you have an input, an output, and a function to perform some action. That function is something you call later when you execute the code. The code logic is essentially the framework that you encode into your script or file. For example, let's consider measurements. I've been working on algorithms for a clothing design software project. Let's say you want to calculate the sleeve length of a garment based on the arm length of a person. The arm length is an input value, and the sleeve length is an output value. This logic extends to other parts of the garment. For instance, the arm length might mathematically determine the cuff width. If someone has longer arms, you might need a wider cuff. This relationship could be expressed in code logic. For example, the input is the arm length, measured in inches, which is an integer value. The output includes both the sleeve length and the cuff width, also expressed as integer values. The relationship might be defined mathematically. Let's say for every 0.5 inches of arm length, you add 0.2 inches to the sleeve length. Additionally, for every 0.2 inches added to the sleeve length, you add 0.03 inches to the cuff width. This logic forms the basis of a simple algorithm. The goal is to translate this into a program. To do so, I provide the logic in natural language and then translate that into an algorithmic expression. With the algorithm defined, I can then design the Python code myself. Here's an example workflow. Define the logic in natural language. The algorithm calculates the sleeve length and cuff width of a design based on the arm length. Identify the input, arm length, integer, in inches. Determine the outputs, sleeve length, integer, in inches, and cuff width, integer, in inches. Define the steps, establish the mathematical relationships, e.g., increments for sleeve length and cuff width based on arm length. This process bridges the gap between conceptual logic and executable code, enabling me to work efficiently and accurately. To calculate garment measurements programmatically, you begin by initializing the necessary variables and defining the relationships between them. Here's a step-by-step breakdown. Step 1. Initialize variables. Base sleeve length, set to 0 or another starting value if needed. Base cuff width, also set to 0 or an initial value. Step 2. Define relationships. Sleeve length calculation. For every 0.5 inches of arm length, add 0.2 inches to the sleeve length. This results in the formula. Sleeve underscore length equals arm underscore length times 0.2 0.5. Cuff width calculation. For every 0.2 inches of sleeve length, add 0.03 inches to the cuff width. This results in the formula. Backslash. Cuff underscore width equals sleeve underscore length times 0.03 0.2. Step 3. Return results. Once the calculations are performed, the outputs are the sleeve length and the cuff width. Python. Def calculate underscore garment underscore measurements, arm underscore length. Hashtag calculate sleeve length. Sleeve underscore length equals arm underscore length asterisk 0.2 / 0.5. Hashtag calculate cuff width. Cuff underscore width equals sleeve underscore length asterisk 0.03 / 0.2. Hashtag return the results. Return sleeve underscore length, cuff underscore width. Example calculation. If the input arm length is 10 inches. 1. Sleeve length. Sleeve underscore length equals 10 times 0.2 0.5 equals 4 inches. 2. Cuff width. Cuff underscore width equals 4 times 0.03 0.2 equals 0.6 inches. The result would be a sleeve length of 4 inches and a cuff width of 0.6 inches. Arm length equals 1 inch. Sleeve underscore length equals 1 times 0.2 0.5 equals 1 times 0.4 is equal to 0.4 inches. Arm length equals 10 inches. Sleeve underscore length equals 10 times 0.2 0.5 equals 10 times 0.4 is equal to 4 inches. In both cases, the formula respects the given rule but applies it over a generalized scale. By creating the proportion 0.2 0.5, you extract the true rate of change per inch, which allows the formula to work for any arm length. It doesn't contradict the original rule, it just makes it scalable and universally applicable. To define a function with a default value for the arm length parameter, you essentially create a Python file containing the code. This file includes the function definition, where the formulas are specified, and a return statement that outputs the sleeve length and cuff width based on the results. The formulas produce the output, which can be executed through the command line. If you want to override the default value, you can simply pass a new argument to the function. For instance, instead of calling calculate_garment_length with the default value, you can call it with a specific value, like calculate_garment_length, 15. This will automatically calculate and adjust the results based on the provided input. The function calculate_garment_length is just one part of a broader set of functions. Rather than creating a single, extensive code file for the entire garment, which could become overwhelming and confusing, it is better to structure the code into multiple functions. Each function handles a specific aspect of the garment, such as sleeve calculations, waist measurements, or shoulder calculations. This modular approach keeps the code organized, reusable, and easier to debug. By isolating each function, you can pinpoint and resolve issues more efficiently and adapt the logic for different designs. Designing garments is a mathematical process that creatively uses math to achieve practical results. Each function acts as a unit of logic for a particular measurement or calculation. For example, you can have separate functions for arm, waist, and shoulder calculations, which can then be combined into a single Python script file, such as garment_design.py. This way, you can call specific functions, like sleeve calculations, without needing to process the entire garment logic. When the codebase grows larger, it is beneficial to split the functions into separate Python files, each focusing on a specific garment area, such as sleeves.py or waist.py. These files can then be organized within a directory, forming a project structure like garment_project/ sleeves.py, waist.py, main.py. In the main.py file, you can import the necessary functions using statements like Python. From sleeves import calculate_garment_length. From waist import calculate_waist_measurement. This modular structure allows you to run all functions in a single script while keeping each part of the garment calculation isolated. It simplifies updates and debugging since modifying one part won't affect others. Additionally, you can reuse the logic and selectively import only the functions you need for specific designs. Because garment design is highly dynamic, the coding process and database must also reflect this flexibility. The calculations depend on both customer inputs and designer creativity. This adaptability ensures the system remains efficient and responsive to varying design requirements. For better clarity, accompanying visuals can enhance understanding, especially when explaining intricate calculations or designs.